Welcome to the next lecture, the first one in module 5. It's all about radio wave propagation. In this module, we will be seeing about ground wave propagation, plane earth reflection, space wave and surface wave, spherical earth propagation, tropospheric waves, ionospheric propagation, effect of earth's magnetic field, critical frequency, maximum usable frequency and virtual height. As an outline of our structure for the fifth module. We'll see what is ground wave propagation. So in general, radio wave propagations can be categorized into four. That is ground wave propagation, space wave, tropospheric and ionospheric propagation. You can see that this category is divided according to the height at which the waves are propagated from the ground. Let us begin with ground wave propagation. Before we go into that, we'll be studying about what is the velocity of radio waves in air. In air, it is same as that of light, that is about 3 into 10 raised to 8 meters per second. In other media, other than air or in free space, the velocity is given by V is equal to C by root of epsilon r. So in case you are getting a question about the velocity of light in ground or in the earth wave or in any other media, we'll get that velocity by v is equal to c by root of epsilon r. Is it visible to all of you? Am I able to draw on the screen so that you can see that? Okay, so let me continue. So I believe that you have done with this. Shall I go to next? So this is a typical representation of an electromagnetic wave. See, we are going to look into some basics of electromagnetic waves transversing across the free space. Or so whenever we say that it is an electromagnetic field, we have an electric field as well as a magnetic field, and a field of wavelength, let us consider, is lambda, is propagating in this particular direction. We have an electric field here and we have a magnetic field which is orthogonal or which is in 90 degrees with the x-axis or the axis of propagation. 90 degrees with respect to the electric field. You can say, if you want, you can just draw a line like this, from this point to this point. This is at 90 degrees. So this is the basic of electromagnetic radiations, that is electromagnetic propagation. Whenever we generate an electromagnetic wave, it propagates along this direction and in parallel to this. So this is how, this is a particular GIF which I have taken from Wikipedia, which demonstrates the propagation of an electromagnetic wave. You could see that this wave is propagating in this particular direction and you have a parallel, a 90 degree orthogonal, this electric field towards this direction and magnetic field towards this direction. You can, in your exams, you can draw this particular uh, to illustrate this particular figure to illustrate how the electromagnetic waves are propagating. That is, you have parallel lines. Shall I go to next? I want you all to be highly interactive. So I've just made this slightly bigger for your better understanding, so that you have this. You see, this is how electromagnetic waves are generated, and you can see how this traveling or this propagation happens. So electromagnetic wave contains both electric and magnetic fields in such a way that they are perpendicular to each other and also perpendicular to the direction of propagation. So you can imagine that you have a three axis, three coordinates x, y and z. Suppose x is taken to be the electric field, y magnetic field, and z would be the direction of propagation. So when this angle is maintained, or this change, or this is called as polarization. We have studied this in our basic classes. Here I have given, this is also taken from Wikipedia. I've given you a simple illustration of how the waves are getting polarized or changing. Vertical polarization and horizontal polarization. We have two different types of polarization, called as vertical polarization and horizontal polarization. So if the waves are traveling in this fashion, and if it is getting changed, you call it as the change in polarization. Okay, this is the basics of ground wave propagation. Are you clear with what is polarization, all of you? So when a wave that is traveling from one point, it hits the earth ground and then reflects, what happens is that there is a change in polarization also. You can imagine you are throwing a ball or something, and what happens when it hits the ground? It changes, right? It changes its properties. Some of these things are going to affect how we are going to deal with our received signals. So let us imagine that there is a transmitter here and a receiver here. A transmitter here and a receiver here, and the electromagnetic waves uh, are directed to move from this transmitter to receiver in this particular direction. So when it moves, it comes across with the different terrain of the earth, and there is a, see, once it hits the earth, it changes, and it keeps, see this, you can imagine that this is touching the earth points, so that the wave that travels comes across with so much of, changes, reflection, diffraction, and so on. So this is the way. Now let me just show you once again that. So what are the factors that is going to affect ground wave propagation? The surface wave, the ground wave suffers additional ground attenuation to the same factor as the free space. The ground losses are caused by ohmic resistive losses in the conductive earth. Surface wave attenuation is frequency dependent, and it increases rapidly with frequency. So one factor that really affects is, one is that it depends upon the frequency, and when you increase the frequency, that attenuation, the ground wave attenuation gets increased. Okay. So apart from the free space, we have another one point here that is called as ground attenuation. So frequency dependency is another one important point. So now we'll see what are the important factors uh, that is affecting the ground wave propagation of electromagnetic radiations or electromagnetic waves. First is the height of the transmitter and the receiver antenna, distance between the transmitter and the receiver antenna, the terrain and the weather conditions along the transmission path. These are the four different factors affecting the transmission of uh, electromagnetic waves while in ground wave propagation. Are you all done with this? Shall I proceed? While propagating along the surface of the earth, waves induces charges in earth which travel with the wave and hence constitute a current. So here we are trying to explain that the earth, no, the ground acts as a leaky capacitor. That means when when the waves are getting transmitted across the surface, the waves, get some charges in the earth, okay, which travel with the wave, and this will constitute a current. We have a small current that is being as a, you can imagine that this is the earth, and these waves are traveling across this. It comes, it induces certain electric as well as magnetic fields. Okay, and this will naturally will generate a small current I. While carrying this current, the earth behaves like a leaky capacitor, and therefore it can be represented as a resistance in shunt arm with a capacitor. This reveals that earth behaves as a conductor, and it may be described in terms of conductivity and dielectric constant. There is a derivation for the relationship between the conductivity and the dielectric constant, but that we will not be covering because that is not in the scope of our study and beyond the syllabus. But you can make a note of this. What are the major factors that affect the ground wave, that affect the waves in the ground wave propagation? Maybe a question. And what is the behavior of the? Why does it induce a charge, or why does it induce a current? And what is the behavior of the ground wave propagation? Any questions related to ground wave propagation? All these points might be valid. So we'll see a very small mathematical equation to find out the field strength in case of ground wave propagation. According to Maxwell's equation, we have d is the distance between the transmitting and the receiving antenna with a wavelength of lambda. In that we have E is equal to neta ht hr, height of the transmitting and the receiving antennas, and the Is is the antenna currents. Neta is the intrinsic impedance of the media. E is also given by A epsilon naught by D. So this is the basic things that we are going to study, and with this we'll be we'll be taking up all the basic points related to ground wave propagation. The equation for electric field, magnetic field, or electric field strength at a particular point D. D from the transmitting antenna is given as E is equal to neta ht hr is by lambda d. Have you all noted this down? Shall I go to the next? Yes. So ground wave propagation for frequencies about 2, space wave propagations for frequencies about 2 megahertz. Ground wave propagation, you know that, is highly limited by its frequency, and you know that is the attenuation increases with respect to its frequency. So here the wave propagation at frequency is about 2 megahertz, is known as space frequencies, and we have two different paths, one through the air and directly, and the other through the receiving antenna. Here we have two different paths. One takes from here. This is the transmitting antenna, and this is the receiving antenna. For example, what happens, and this is the earth. So you have one wave coming directly to here, another one hitting here and coming back. So these are the two types of wave paths that is being taken in space wave propagation. Is it clear? Space wave is made up of two components. One, the direct and the ground reflected wave. There is always a phase shift between these two component waves because of two signal paths and they have different lengths. So we have this transmitter, receiver. This path, let us call this as R1, and R2 is the one that is being reflected from here. So the distance, the value of R1 and R2 is different. So it travels two different lengths. We'll be studying this in the next coming slides. So that there is always a change in phase or phase shift. We'll be studying about the effect of phase shift in the electromagnetic fields, and we'll be studying the distances which the wave travels in two different paths. So this is called as troposphere, the 16-kilometer radius from the earth. This particular one, blue color, which I have denoted by blue color, this is troposphere. This is the earth, and this is the range where we are going to transmit our space wave propagation. So let us consider a wave R1 that is being transmitted from the receiver to the transmitter to the receiver. So in this case, see, this R1 is a direct ray. It is getting transmitted from this transmitter to the receiver. R2 is the ray that comes after deflection from the earth. From this point it reaches here and it gets deflected. So R1 and R2 are the two things. We'll take this to be the distance D, is the distance between the height of the distance between the transmitter and the receiver. HT is the height of the transmitter and HR is the height of the receiver. Let us consider this angle to be theta. So we have this angle to be theta and this also to be theta. This is from the normal. This is the normal. So what happens is that this angle will be 90 minus theta and this angle will be 90 minus theta. From this we are going to derive the equations of R1 and R2 and the path that is being transmitted, the path that actually that wave takes, that is R2 minus R1. Okay, this is the difference of distance between the signals taking two different paths. We'll use the basic trigonometry to calculate both these values, fundamental trigonometric equations. So using our Pythagoras theorem, we'll get this R1 square to be equal to, we have it like this, height HT and HR, and this is D, right? This is R1. So here if you put a line like this, and this will be theta, this will be R1, right? So R1, this R1 will be, R1 square will be this value. This is HT minus HR. HT is for this whole one. So HT minus HR plus D, this is D, distance between D. So R1 will be given by D square plus HT minus HR the whole square. Now we'll take this and we'll find out R D into root of, taking this D outside, HT minus HR by D the whole square. Okay. Using this binomial expansion, 1 plus, see d is much greater than this value, right? We don't take small distances between, much greater than ht, and d is much greater than hr, because our minimum distance between the transmitter and the receiver would be much higher. We need at least 100 km or so range for transmission. So in that case, what we'll do is that we'll use our binomial expansion. Root of 1 plus x is equal to 1 plus x by 2, and so we'll get the value of r1 to be, we'll get the value of r1 to be equal to d plus ht minus hr the whole square by 2d. r1 is equal to d plus ht minus hr the whole square by 2d. Okay, have you all understood? Is there any clarification? Any doubts? Are you all listening? Are you all clear with this? I'm not really able to understand whether you guys are listening or not. Please be as interactive as possible. Amrita, are you here? Okay. So the next point, is it legible now? Are you able to read it, all of you? You want me to read it aloud? Have you all noted it down? So space wave propagation continuation, we'll see we have found out the value for R1. Slightly bigger, I've repeated the slide. So you get the value of R1 to be approximately equal to D plus HT minus HR square by 2D. So what is the problem with R2? R2, it comes here and then it gets reflected here, right? So R2, you have this path plus this path. So what happens, it is HT plus HR, right? So similarly, when we find out the value for R2, R2 is these 2 points, these 2 things, the total path traveled by the ray after it gets reflected from the ground. Okay, so with this particular normal, this is theta, this is theta. So this is R2 will have this value. Say here, this you can put some other value, say D1 or D2. So D1 plus D2 will be equal to D, D2 is equal to D, and R2 will be equal to, R2 square will be equal to HT square plus D1 square, say for example, plus this part. Okay, this part, that is D2 square plus HR square. HR is the height of the receiver. Same way, what we'll get is that R2 will be equal to, R2 will be equal to D1 plus D2, D square plus HT square plus HR square. And on solving this, similar to what we have done for R1, we'll get R2 is equal to ht plus hr square by 2d. Am I right? Are you able to get me? So we have found out R1 and R2. Now what we are going to do is we are going to find out R2 minus R1. We are going to subtract this, and what we'll get is that R2 minus R1, we'll get it as 2 times the very important equation, the difference in path. The difference in path between the ground wave that is reflected through the ground and the direct wave. So the value is given as R2 minus R1, which is equal to 2 times HT HR by D. Have you noted it down, all of you? The difference in path. So next is a very important question that has been asked continuously in your exams. In most of your exams, you find this question. Even the previous year, we had two questions in module 5 based on this particular thing. That is the line of sight distance between the transmitter and the receiver. Okay, here what we are doing is that we are finding out an expression. This is something which you have already studied. Maybe you have studied in your school days and basic physics and so on. But anyway, here you commonly get one question like derive the expression for the line of sight distance between the transmitter and the receiver antennas, or we get some problems based on this. Okay, so let us consider HTB, the size of the height of the transmitting antenna here. R0 is the radius of Earth. D1, see, let us consider this transmission is happening in a tangential form where this particular line, this particular line touches at one point in the Earth. Touches at one point in the Earth. That point we can call it as something like C, or that point we can call it as B. A, I'll put this as A, I'll put this as O, the center of Earth as O, and this as C. Okay, so we have A, B, C, and O. I'll write it a bit more clear. This is A, this is B, this is O, and this is C. So this OA, the distance from this particular point, the center of the Earth to the point, the tip of the height of the antenna will be equal to R0 plus HT. OB, this point to this point, this B, is equal to R0, and OC will be equal to R0 plus HR, the receiver, at the height of the receiver antenna. Okay, so with this we'll be able to calculate the line of sight distance between the transmit and the receive antennas, and we'll be having problems based on this. We'll do that today. Have you all noted this down? So now from the Pythagoras equation, this R0 plus HT square is equal to R1 square plus R0 square. This is R1, this is the distance. What we have to find out is R1 plus R2. That is the line of sight distance from this point to this point. Okay. So what should be the height of the receiving antenna? We usually get so much of questions related to that. On solving this equation, what we'll get is that R1 square is equal to 2 R0 HT plus HT square. So you know that HT is too small when compared to the radius of the earth. Okay, that is around 6,370 kilometers. You need to do this with, you need to make problems out of this. Need this value to solve out so many problems. We approximate the radius of earth to be 6,370 kilometers or something related to that. So now R0 plus HT square we have done for R1. Now we are doing it for R2. Similarly, what we'll get, R2 square is equal to 2 R0 plus 2 R0 HR plus, so this is, sorry, this is HR square, that is equal to 2 R0 HR. Similarly, we are approximating this R0 to be much greater than HT or HR. In that case, we'll find out both these values, R2 square and R1 square. So this R, total distance, line of sight distance R, which is R1 plus R2, will be equal to root of 2 R0 HT plus root plus 2 R0 HR, all inside the root, or in other words, this one. R is equal to root of 2 R0 root HT plus root HR. This is a very primary and very important derivation which you can study with ease and you can score marks. For the previous year question paper, this was asked for 7 marks, and the other 7 marks, that is A and B, was a problem based on the same equation. That problem is what we'll be seeing in the next slide. The problem that was asked in your previous university question paper. So R is given by root of 2 R0 into root HT plus HR. Have you all noted this down? Shall I proceed? Yes? Yes or no? No response. Now Anisha, please tell me what is the equation for R. We have just derived. Now R is equal to, Anisha, are you here? Amrita, then tell me what is R. Tell me what is R. So long. Root of 2 tell me what is R. Somebody else tell me now what is that R very fast. R is equal to, Amrita, 2 R0 into root of HT plus root of HR, right? So what is the value you are getting? R naught na value is 6370 into 10 cube into 10 raised to 3, the radius of earth. This you have to know. You may be asked in the exam without these values, because last time it was asked without values. So what is the height of the receiving antenna? Minimum height required. Hisham, are you there? Did you get any answer? Root H R is equal to R by root 2 R naught minus root HT. Am I right? So what is the value of R here? 80. 80 by root of 2 into 6370 into 10 raised to 3 minus root of 100. What is this value? Root of 2 into 6370. This question was asked in your previous university exam for 7 marks. 7-mark question. So simple. Anybody else? Any other answer? Okay, I'm proceeding to the next. Okay, so a similar question to what we have done previously. We have a 10 gigahertz microwave link to be established on the surface. The radius of earth is given. Not in every question paper you get this value. So in case you are not given, you have to substitute with 6370 kilometers, because even in the previous year question paper we didn't have this value given. That is this value R naught. The value of R naught is given to be 6370, and the distance between the antennas R is given to be 60 kilometers. HT, the height of the transmitting antenna, is 60 meters, and you are asked to find out what is HR. The same as in the previous question, you can ignore this value. 10 gigahertz is just given to confuse you. So what is the value of HR? What is the answer you have got? Anybody who got the solution for HR? What is the value of God? 59.37. Seven three. Any other answers or anybody with different answer? 7 3. Are you able to hear me? So accordingly, we have this height of the antenna to be approximately 60 meters, right? Yes. So you can expect similar problems in your exams. We'll continue our session on Monday also around the same time. Is it fine? We have only a very few more topics to be done. I hope by Monday I think we can wind up. Any clarifications or any queries? Any doubts? All of you? Shall we wind up for the day? So thank you all. Thank you very much. We'll have our next session on Monday. I'll post the Google Meet link by Monday. Okay. So thank you all. Thank you very much.